I the next 40 to 45 minutes, I would like to give basically an introduction, right? It's going to be a small bird's eye view of steel concrete composite structures. There are going to be many occasions where I will talk about much deeper fundamentals of steel concrete composites. There are so many concepts are there in the design of bridges. A small introduction about why what are the merits of steel concrete composite bridges. Of course, sir, the participants should feel that this is not saying that something to do with a PR for steel or steel concrete. No, concrete is a wonderful material. Steel is a wonderful material. We are here not to say that this is the best, will solve all your problems. No, this is another a structural entity which can be really used. It gives you lots of possibilities for you. That's what is it? For example, concrete. We people are really great, and priestess concrete. I mean, every aspect of it is done. Steel, of course, yes. Steel concrete composite also. A lot of them have been done. But then, uh, to the information, I say usually the steel concrete composite bridges have an edge in the strength to weight ratio. Okay. Also, if you take the, I'm sorry, it is dead load or live load. Okay, lower dead load to live load. So sorry for the typo. And you have a flexibility in the layout of spear, right? Piers. Now, when I tell people, if you take a span for concrete and then you compare with steel concrete composites, possibly not a right comparison because of the lower dead load. The spans can be little larger in the case of steel concrete composites, and if you have enough headroom, we can also go for the trussed composite bridges, which we have one in Mumbai. Um, Forgotten. By the time the lecture ends, I would get it out. Okay, so less constrained on the flow of the traffic. I will show you when I walk through. Is it how quickly we finish the work on the ground, and then we get over on top of the bridge to do the other things. Okay, and a lesser congested site during construction. For example, the experience of us is uh, only for the piling, right? Only for the piling, we will block that too face by face. Once the pile cap is done, and if you use a steel, it's simple erection of the pier. We will remove all the space free for traffic. So that's what we mean by less constrained on the flow of traffic because everything is going me on top. You can even do it at night. And of course, there is something called penalty cost, right? I think we are not sensitive to that. There's something called penalty cost. What's the community pays for the construction of the bridge? The community pays quite a lot in terms of, um, disturbance, in terms of detour, in terms of more fuel to go around, things like that, right? See, these are the few advantages that you can always have. Anyway, I will get into the concept. This is for the young people, the designers, and thing. So, what I will one second, I'll say. Right. What I will try to do is, what is that the concept, right? What is the concept of this? First, I'd say a plate girder bridge, right? So you have several um, plate girders, a series of plate girders, usually five, four, three, depends on your number of spans um, that you're going to build. You can adjust the number of plate girders. Normally, it's about 2.5 is the spacing of these plate girders. They can rarely roll sections are used, right? You can use roll sections, but then there is a bit of difficulty in getting the sections right. So many of you may know that um, you you can get up to 600 depth of steel beams, but then to made to order, Jindal can make about 900 maximum in India. Right. So usually these plate girders are three-plated systems in which I have a web plate and a flange plate connected together. This thing. That is the basic load workhorse. Now, on top of it, I put concrete, right? We put concrete, and this is a bi-material system. I have steel and I have concrete on the top. Now, the modulus of the concrete, as you know, is less compared to the modulus of steel. Correct. Now, what happens if I apply a load on the deck? The load goes to the deck first. Okay. Now, depending upon how the deck and the beam are connected, a composite behavior occurs. Okay. Now, why is that? How the word I'm saying is what is the type of connection between the steel and concrete? The reason is that sheer rigidity always decides what sort of a behavior you are going to get. Right. Now look at the you can see this figure. You can see I have steel. Okay, normally the concrete will be under compression and the steel will be under tension. Not necessarily, right? In the composite action, and depending upon the relative, depth of concrete, which we call it as ds, right? We call it as ds, depth of slab, and this is usually called depth of the steel, right? Depending upon these two, and the material concrete, strength of the concrete, the strength of the steel, the the neutral axis can be in the concrete or in the steel. See, normally we can take by for most of the practical points, the compression is taken by the concrete and the tension is taken by the steel. Right. Now, what is that? These things I have what's called the shear studs, right? Shear studs, right? Shear studs, and I'm going to show you the okay. I'm going to show you how the most important part of the steel concrete composite design is the designs, the design of the shear connectors, correct? I've always, argued to my students, right? Chicken or egg, which is first? And the parallel question is moment or shear, which comes first, right? Everybody says, sir, moment and shear, because I tell you, only because of the sheer rigidity, the moment is taken, right? In the next lecture, I'm going to take it on open web girders. I will show you, right, how the sheer rigidity is primary reason for the moment resistance to get developed, right? So for the time being, I would stop that the connection, the shear connection between the steel and concrete decides the entire performance of that, right? Now we will be, learning it a little more detail so that at least some information is retained by this lecture, right? Now we start, there is a steel beam, there is a concrete deck slab, and the shear connectors integrate steel and concrete, and that is the system, correct? Now, in the bottom, you can see when they bend together, both of them will try to act together, right? That's the point we say. So the load flow, if we see, the live load comes onto the deck goes to the plate girders. The plate girders span between the piers. So the load goes to the pier and to pier to, pier cap, pier to the foundation. That's the flow, and we are talking about the superstructure of this, right? So I can have very nicely, if I have a headroom, I can use a steel concrete composite truss bridge. Again, the same concept. I have an RC a deck. Of course, I'm not talking about the toppings that we have, the black top, the weathering coat, and this it is implied here. So I have a deck slab and supported by a truss system. Now, this is integrated using the shear studs. I don't know whether you are able to see the shear studs. Don't worry, I'll be showing a couple of more examples for the shear studs. Right. Now you can see is same principle. Two different systems, one with a higher modulus, another with a lower modulus. One is very good in compression, another one is good in tension, but okay, I can make it good in compression also. So we are trying to integrate using the shear connectors. Okay. Now the system looks like this. The system looks like this. So you have a deck slab and you have a truss, um, which takes, of course, I say in general, there is compression in the concrete and tension in the my truss systems. Of course, in the bottom card, and you will find the web members vary as the shear force that comes on the system, right? So this aspect of how the flanges take the load and web members take the load, or the chord members, I will cover in the next lecture, right? So I have given you a brief of the steel concrete composite systems, in which two different materials, both are good in some respects, are integrated using what is called the shear connection. Okay, with that introduction, I will go and show you uh, the chicken comes first than the egg, or something. I want to say the sheer rigidity of the system is going to dictate how a steel concrete composite systems behave together. Right. Now I say, what is the role of shear connectors? So probably I would put more focus on the shear connectors, right? Or more for shear connectors, because that is the one which is going to decide on my behavior. Correct. Now, again, the same example here. I have a steel concrete, I'm sorry, concrete. I have a steel element and I have a steel concrete element interface, right? Interface. Now, when I apply a load like this, imagine when I apply a load like this, now the deflection of the steel, because the steel has more modulus, it will deflect less, compared to the concrete. However, the concrete being less in modulus will try to bend in the curvature of the steel beam. That's the thing. Now, for a minute, you reverse. You imagine the top one is going to be concrete. I'm sorry, steel. I'm giving a situation hypothetically. So let's say I have steel beam on top, and I have concrete. You will find a separation that takes place between these two members. I hope you have got, this is steel and this is concrete. So since the material underneath has a lesser um, modulus, it will deflect more, compared to the steel. So we have got to, let me erase this, because this is going to, um, sometimes going to, disturb the learning of the students. I'm only showing that one example in which I'm saying that concrete is at the top, um, concrete is the top, and bottom is steel. Right, now you look at here. Look at here. There's one thing, something's very interesting. Take the concrete. Take the concrete. the concrete top will be under compression. The concrete bottom will be under tension, right? Now, the steel top will be under compression and the steel bottom will be under tension. Now, my interest is this one. My interest is going to be this one. What is that? The interface, right? Now, because one is in tension, the fibers are going to get extended, and on the top of the steel, it is going to be compression. So they are going to get shortened. Now you see an interface, a movement in both direction or in the opposite direction. Correct. So this we call it as the shear surface, shear interface between steel and concrete. Now, what happens is that imagine if I apply a grease, right, between the, say, let's say I will call you, please focus your attention on the interface. Okay. So the whole part of our, composite design is going to be on the behavior of the interface. Now, we learned that since the compression tension is at the interface, they will try to slide across each other because one will be extending its fibers, another will be shortening its fibers, right? Now, in order to arrest the do, I insert a dowel, right? I insert a dowel. Let me see, go and see that. Okay, I'll take a red. And this is a dowel for us, okay? Right. So this dowel is called the shear connector, right? Why? Because you can see here, right? You can see here the interface slip, the slip between the interface of concrete and steel is actually resisted by this dowel, right? By the dowel action, correct? Now you can see here, I have given, it is very difficult. So for example, if the number of shear connectors is very high, I'm only saying it qualitatively, you will not see any slip here, correct? So the displacements that I see between the steel and the concrete surface, I will call as slip, right? So if I have zero slip, if there is absolutely no slip between the concrete and beam, it's because I have provided my shear connectors in such a way that the interface behavior is highly rigid and literally, not, there'll be small slip, literally no slope, no slip can occur in between. So what we are seeing is the the slip between the concrete and tension depends on the shear rigidity that we are going to have on these interface. So that's the fundamental point I want the participants to take. So there are several ways you can put the double action. You can see here in the elevation, I have a steel beam, and at the interface, this is concrete, this is steel. I have the dowel called the shear connectors. Now, we are going to concentrate on the shear connectors, saying that why the shear connectors are much more important in the composite behavior, right? So we have two types of connectors. One is called the rigid shear connectors. So what we do is, let's say we have a T section, right? In the earlier slide, I show you, you have a stud shear connector. This is called a shear stud, correct? So this is one way of the connection is being done between the steel and concrete. Now, I can have a T section as the shear connector, right, between the slip and the concrete surfaces. But I feel not a good idea. This normally I will come to the reason why. That is fine, but I would not prefer, and many times. Next, I can put a channel. They are very cheap actually. They are very cheap, and because the shear studs that I showed you are a bit expensive and they need some kind of a mechanical and electrical device to fix it, and these channels can be easily welded onto that. The other one is I can have a built-up section you can see in this elevation. All these are called rigid shear connectors. Rigid shear connectors means they give um, an interface behavior in which there is absolutely no slip between the concrete and the shear connector. If at all the failure happens in the interface, it has to be the failure of concrete. Crushing of the concrete using the interface, that can only happen in the case of rigid shear connectors, right? Also, I told you one word that these kind of shear connectors, maybe I may not choose it, but then I go to the other one, which are called flexible shear connectors, right? So what happens, flexible shear connectors is they have a tendency to, really little bit bend. I told you the other one, the shear studs can bend a little, correct, in the load carrying. That is good for me. Sometimes, after all, I want to design flexible, structures that gives me adequate warning, and we say we have to have structures that has ductility, and then it shows any distress, so I can correct it, and I don't want any catastrophic, boom kind of failure, right? This is one type of flexible shear connectors, and this is a channel shear connectors, and you will be surprised that in the last time, in the last slide, I showed the channel shear connector here, which I showed. I will not prefer. Then right now I am coming and saying this channel connectors, which is slender, is acceptable to me. The reason is very simple. Right. See, you can see here in this particular case, I am putting the channel shear connectors this way. But in the earlier case, I had put the shear connectors this way on the interface. Let me show the interface surface. So on the interface surface, here I have put the channel in the vertical direction, and the earlier one I showed the channel put in this. Now, why this is important? Let me just have a quick fundamental of why this that vertical element is needed. Right. I will show you. Right. This is my flange. Right. This is my flange. I'm showing in the longitudinal direction, sir. Right. I'm showing in the longitudinal direction. And this is the interface, right? I will just show the free body diagram of the, for the benefit of students, I will say I have an I-beam. Now I am concentrating on this region. I'm concentrating on this region, right? Now, what is the shear equilibrium for me is that the flange has a force, okay? Just a minute. Yeah. Now, the flange has a force, right? That force is transferred as shear in the interface, right? That is what we have already learned. Even for a simple plate girder, three-plated system design, what we do is we find what is the force coming on the flange. Because of the high stress and more area, the flanges will have a lot of compressive force, or tensile force. So what we do is to transfer the flange force across the interface of um, flange and the web. We designed this, right? We designed the well. Very similar to that, if I draw the free body diagram of the flange and the interface, this is um, um, the equilibrium. Now, the elements are not in equilibrium. The elements are not in equilibrium. Why? because sigma H is satisfied, but sigma M is not satisfied. So these two pair of forces, and they are little separated, they're going to cause you um, an anti-clockwise moment. It is very small anti-clockwise moment. Of course, I'm not saying there's a primary moment. It's going to cause a small anti-clockwise moment, right? Now, what happens is that to counteract this, there will be a clockwise moment. I'm sorry, there will be a clockwise moment, right? That will equilibrate the interface spheres. Now I can say in the entire system, there is the horizontal equilibrium is satisfied at the interface, and moment equilibrium also the satisfied interface. Now I want you to look at this one. I want to look at the vertical component of the vertical component. So at the interface, my shear stud will be sheared, right? Basically because of the shear. But because of the equilibrium moment component, there will be an upward force also coming on the top of the connectors. So if you take a connector, there will be a force that shears it because of the interface, the double action, and there will be an uplift force, right, because of the moment equilibrium coming. That is why what we say is a very good shear connector should have an element which will stop the separation of the steel and concrete interface because of the moment equilibrium. Now, in the earlier case, right, I said this is no for me because there are no elements that are going to stop the separation between concrete here. However, purely by friction of the surfaces, it is going to give. However, if I put a channel like this element, right, it is going to, resist the upward separation, and it will also resist the shear. So in both cases, I would always prefer an element, right? I will always prefer an element which has a projection on the top, which will actually will help me to provide that. Right. Now what we have done is we are talking about shear rigidity, and then I said because of the shear interface small um, eccentricity, there is a moment which is resisted by the head of the shear connectors. Okay, fine. So we saw two type of connectors, right? Ductile, the one which I showed you, the channel standing straight, and the stud shear connectors. The other one is the block shear connectors. We say a T and a channel putting in the horizontal direction. Now, this is the behavior. You can see here, the rigid shear connectors give you a very high strength, but their failure is explosive. So this failure is very similar to my rigid connector behavior, right? Rigid connectors will fail suddenly. They will separate off at the interface. I'm not saying that they're going to fail at they have more, strength. As the load increases, when they reach the ultimate stress, they will just separate. So this is the rigid. However, the flexible shear connectors, right? The flexible shear connectors will give me a very nice behavior in which I can see the slip. You can see here there is a slip between the interfaces, still intact, still shear is being carried. So that is the reason that we say in most of our application, a ductile shear connectors is always preferred because it not only gives me the required shear strength, and also it gives me the flexibility of that. Right now, if I can design a beam in which the shear rigidity is very high and absolutely there is no slip, and you can see the bending. This is the strain diagram, which is one for the entire beam. However, if there is a slip which I allow, then I'm allowing small, tension compression system. And if there is concrete, if this is concrete, the tension part will be neglected as we assume it as very is cracked. So even here you can see they bend us to independent systems. Yes, I have now developed, quite a lot on the importance of shear rigidity and how the shear connectors should have a head or an element that are separate. Right now, this is the degree of shear connection. Again, I'm telling you that this is the one, this is two, and this is three. So this again, I'm summing up our learning, right? I can, make a system in which is there is literally no slip. There is slightly slip. I'm saying for theoretical, I say there's absolutely no slip between the steel and concrete. So I can have partial shear connectors. That means as long as my strength is satisfied, I can allow a bit of slip to happen between the steel and the concrete. That's fine. Because if I can satisfy, say, mind you, these are all in the ultimate state. Of course, in the serviceability states, we don't go up to this. So we are in the elastic range. So we use it the normal transform sections principle that is given in textbooks. So I'm talking about ultimate. So we have a partial shear connectors, and of course, if I apply a grease, there is no composite action. Of course, this is only a theoretical proposition. This is only a theoretical proposition, and usually these two are the one which are mm, design on that. So steel is steel, concrete is concrete, but the way they are connected by the shear connected dictates what sort of a behavior. Right. Now, for those of the young people and the engineers, I'm going to give you a walkthrough of the construction of a steel concrete composite bridges. So I give you a little bit of fundamental of that. Right. Now, this is an example, right? So this we are going to, connect, make an ROB, right? See here, I have my, the pre-stressed concrete span is just ending a short span, and I have a railway line and I need to cross. Now the word ROB, many of the participants must know, for the railways, they will take the rail level as their reference, right? So anything is goes over that is ROB, road over bridge. And if you keep something underneath, it's called road under bridge or UB, right? So I'm going to construct an ROB. Now, what I can do is I cannot put all the, scaffoldings and everything, because it may take 10 days. You can complete, but it is not about the 10-day, the blockage will cause crores of loss to the railways, right? So it is a busy way, absolutely no possibility. So what we are going to do is, okay, we get what is called a line block, right? The line block is you ask the railways, they will give you under lean time. Okay, take 8 hours, right? And what happened within the 8 hours, we have to move the plate girders over this. This is one of the sites which is getting prepared for the launching during the line block. Okay, so you have to keep your crane ready. You can see the plate girders are all the 5 plate girders are ready, and there are 2 cranes which are going to lift it in tandem. So imagine here, this is where my bearings are going to come. Okay, next is, right, I have put the bearings. I lift one by one. I lift one, there are 2 edge girders and 3 middle girders. So we will lift it and put it in place, right? This is one lifting. You can see here, this first girder, the other girder is ready. You have 2 cranes lifting in tandem, one here, one then. Then the red line is the one where I intend to place this. Usually we'll start from the extreme one, right? We'll start from the extreme one and then we keep on adding towards the lifting side, right? Due to what is called the LTB, you can see here the once the plate girders are placed, these are the bearings, right? So it is placed on the bearings and the bearings are locked, right? The bearings gives us the rotational freedom and arrest it. So there is no movement is allowed and it is blocked using sometimes with a wooden sleeper or wood or any other system that blocks it, right? Now, sometimes what happens if you are, even in this project, we had the problem of LTB, the lateral torsional buckling. Sometimes we do a twin girder launching. That means one supports the other, right? Now, the LTB is the tendency of the girder to go sideways, right? At the middle due this thing. So this is avoided by a twin girder launching, right? Now, once we have launched all the 5 girders, place them on it. Now all the 5 girders are placed. This is girder number 1 and this is girder number 5. These are edge girders and the middle girders. And now you can see here, once the line block time is over, we have bridged our this thing. This is about 48 meters span and a 55 degrees skew. You can see here that the to the line the bridge is 55 degrees skew, and I have finished all the 5 girders on top. And look at this, what shear connectors I have provided. I have provided channel shear connectors very close, about more than 6 mm. Right, now the cross girders come in place, correct? Period. There is no line block is needed, but only thing is the communication from the railways, which is the lean time with which you can work. Okay, once it is done, you can see here all my 5 girders are there and with all the shear connectors, and I put all the reinforcements, correct? Now, what I can do is there is 2 way I can design the composite, steel concrete composite bridge. One as a composite bridge, another it's called a non-composite bridge. Okay, now the difference is if it is a non-composite bridge, concrete is only as a weight. It doesn't offer resistance, right? It is only on the load side. But if it is a composite design, the concrete at the initial stages acts as a load, and once it is set, it is part of the resistance. So it is always better to design a steel concrete composite action so that you utilize the best of concrete and best of steel. Because otherwise, you can take the entire concrete load as a load to be carried by the plate girders, and we put minimum shear connectors, right? After that, concrete is done, very easy. So we can pour, I always say the word concrete is poured like water, then you can fill it up, right? So I give a bit of a nice walkthrough of how a steel concrete composite bridge is built. I have a span to be there. I'll get a line block from the railways, lift girders one by one within the time window. Once they're dead, the traffic is resumed. Then lean period, I put all the cross girders. And once the cross girders in top, I'll put all the shutters. Sometimes it is wooden planks or sometimes steel deck sheets. Right. After that, I put the concrete and said, of course, you're ready for the traffic. Right. Now, I will take you through the simple design of uh, a steel concrete composite. Let's say a plate, a steel composite beam for a bridge. Okay. Now, what you do is there are 2 different ways you can now you can see here. This is basically is from IRC 22. where I use a rectangular stress block, right, with the value called lambda, right? So your neutral axis depth is xu, but your stress block will be dictated by what's called lambda times xu, correct? So if you go to EC4, they will use a rectangular block, right? They will use a rectangular for the full depth up to XU, and they use 0.85 times, right, of FCY. They use cylinder strength, right? Now we have three options are there. Option one, parabolic, which we use in IS 456. This is EC4, right? This is EC4, and this is IRC 22, but basically very similar to EC2, right? So three distress blocks. So what we have done is in IRC 22, we use this, and 11384, we can use this. Now you have, the designers have a possibility that you can use the rectangular, I mean parabolic stress block also to find out the capacity. Okay, now the simplest case I've shown you that the neutral axis is in the concrete. So this is just to teach you how you can do one particular design. I have done the design, I'll show you. So what are the other possibilities? The first possibility, let me show with a blue. The neutral axis can be in the concrete, the neutral axis can be in the flange, and the neutral axis can be in the web. Correct. The three possibilities will come. Why do they like that? It depends on the relative strength of steel and concrete. What is the principle by which we do? For at the ultimate state, all members are stressed to their maximum. You can see here, I have taken the value of entire steel to be Fy, right? That means it is yielded. And you can take my stress block, it has reached, say, 0.0035. So what we do is, if I take the shear connections, I would take it, it will go to the ultimate. So in the ULS design, ultimate limit state design, we assume all the materials reach their maximum yield stress. At that position, we will find um, uh, the the moment capacity. Okay, a small example I'm showing. Right, I'm not going to do the shear connectors, but I will assume that it is no slip, right? No slip, full shear connection, right? No slip at all. So I don't have to bother, but I have provided enough amount of shear connectors. So I'm not going to design that, but I'm going to design the beam, right? So in IS 11384, we call depth of slab, and this is the steel beam. And in this particular case, your neutral axis in the web of steel beam, right? Now, what you have to do is, there is a much important part of the design is a value called BEF. This is called B effective, very similar to the B effective that we do in the T-beam design of reinforced concrete. Very similar concept. However, if you see the code, there are three different ways of finding the effective width, or the width of the slab, which is going to act along with the steel beam, has to be calculated. Right. What is this? It can be an end beam, it can be an inner beam, and it can be an outer beam. Right. What is an outer beam? There is an overhang. What is the inner beam? There is no overhang and only inside. What is the inner beam? There is concrete on both sides. Now, the the effective BF is not decided by the cross section alone, but in the span. Right. What we do is, we take the bending moment diagram, right? It is this is taken like this, and based on the bending moment, diagram, we say we locate certain points. If it is a mid span, if it is a support span, if the next mid span, the support span. So we identify different regions, and we use the L effective um, to find out the B effective. Why I'm saying is, in the example I'm going to show you, I have already used the value of the B effective as 2750. So I'm not going to show the calculation, but I only say the B effective has to be calculated depending upon where you are going to do the design of your, right. Now coming to the simple problem, so every one of us can relate, right? So what about the shear connected? Full shear connection. I don't have to worry, there's no slip, fine. Now my concrete is 30 MPa, my steel is 355. The design resistance, the capacity, single, shear stud is 74 with a 32 dia, which is the stud capacity. I have given you the factored bending moment and factored shear. Thickness of the flange and everything, all data is here, right? Now, both of them are acting together because I provide enough. Okay, next thing is, now I come to the stress part of it. What did we see? At the ULS, I assume all the material reaches their maximum, correct? So I draw the maximum concrete and my steel thing. Now, what is the governing principle for me is the compression must be equal to tension. Because what is after all a moment? Two equal and opposite forces separated by a distance. Correct. Now, the compression component has to match the tension component. Right? If the compression is
Dr.
F.
Arul, I have to
Yes, sir.
intervene. Actually, we are running out of time. Probably we have to run fast because it is already
Yes.
three past. It is 3:07 now. Kindly.
Okay. Sir, 2 minutes, sir. I'm cutting end of it. Uh, I'll just 3 minutes. Thank you for reminding me. Now you can see here, I can take the two parts. You can see the compression and tension. Right. Now, I don't know. I make an assumption. To find how. So what I do is I'll take the full strength of concrete, that FC. I take the B effective in 0.36 FCK. I find this is my compression capacity. I find steel, and this is the steel capacity. Now, what is governing to me? This one is going to govern to me, because why? That should, compression and tension should match here, right? Now, once I know that, how do you find my XU? I find the steel force and I equate the concrete force, correct? And I get XU. I calculated for this problem XU, which comes 80 mm from the top of concrete, right? Now, very simple. I have already got the neutral axis XU, which is 80 from the top. So that is my stress block. I know what is the force. So this force and the compression and tension should match. So my moment capacity is simply concrete or steel separated by the distance, and I find the moment capacity. Very simple. This is a case of fully shear connections in which I can compute this, right? I've checked here for bending, and I find my utility ratio is 0.83. Okay, satisfactory design. Now, when I come to the shear design, one of the advantages that I have is only the shear part of the steel web is taken as the element which offers the shear resistance. Usually we disregard, if at all there is a double action due to the small reinforcements, and nothing, no contribution is taken by the concrete. So what I will do, I'll find the slenderness first to check whether there is a buckling of my web. It is less than 67, so no web buckling check is needed. Then it's going to be a plastic shear. So I find the shear area and I find the state capacity, and I find my utility ratio is 0.38. Great. So there is a possibility for me to reduce my web area because my utility area is 0.38.
We are building all these three types of bridges. And in the first case, we have redundancy. In the second and third, we don't have redundancy. But they look different and they have different structural behavioral concepts, which I will also dwell on. And we are looking at trying to induce inelastic actions, desirable, stable inelastic actions in certain members. And the question was, where do we induce those in bridges? And when you look at building design versus bridge design, and that is the biggest difference between the two. In the building, the horizontal member must see the damage, and in a bridge, it will be the vertical member that will see damage. And that is the big difference between seismic design of bridges and seismic design of buildings. And one must have this distinction very clearly. So if you are a bridge designer, you will go and inspect the site when the vertical members are being built, definitely. And when the horizontal members are being built, you will notice that it is so critical that you will be there at site. In a building, in most cases, we are not visiting the site when the vertical members are being built, and we are visiting only when the horizontal are being built. And so we are putting the vertical members in jeopardy by not doing good quality supervision. So once again, in bridge, damage will be in vertical member and not in horizontal member, because we cannot damage the horizontal member. In a building, the damage will be forced in the horizontal member because we cannot afford the luxury of damaging the vertical member in a building. We talked about discontinuous bridges requiring a lot of bookkeeping, and continuous bridges requiring relatively lesser bookkeeping. So we would like to see as many more continuous bridges as possible in strong seismic areas. So this is where I was, which I said that we are looking at 5 components of a bridge, and definitely not the superstructure. It is so stiff, the stiffness is so large that you cannot damage it under bending action or shearing action. And soil, definitely you don't want to put a bridge on weak soil. So the question is, of the remaining 3, where will the damage be? And I'm trying to now exaggerate the diagrams here so that you will understand that no soil and no superstructure damage. The remaining are bearing, substructure, and foundation, right? One thing that was taught to us when we were younger is the person helping should be stronger than the person receiving help. From that principle, the foundation has to be stronger than the substructure. And so I will rule out one more. That means foundation is also out of this list. The competition now is between 2, bearings and substructure. So let's go forward and see which of them will win. I talked about the number of pieces in a bridge. If you have too many pieces, you have too many bearings also. And one of the issues that is plaguing designers, bridge designers, is which bearing to use and where to place which bearing. It's still a crisis, and I believe that it is time to sort out this from a very fundamental behavioral point of view. What is good for thermal expansion and contraction is also good for the purposes of seismic shaking. And that is why we want you to recognize 3 types of bearings: restrained, guided, and free bearings in the horizontal direction. In the vertical direction, we pray that we are not having uplift, because most bearings that we get do not have the capacity to carry uplift in tension, but they can carry a lot of vertical load, many of them. So the key issue here is that you have to choose your bearings in such a way that you don't induce stresses during the normal functioning, that is when live load is passing on it, or under dead load self-weight action, or under temperature expansions and contractions. Same orientation of bearings will still be our friends for the seismic action. You will notice that the more exotic will be the spans. We just saw one skew bridge across the railways, and if you're going to design the bearings the same way as you design normal straight bridges, then we are going to definitely have challenge of unseating, and that is why we need special attention on the orientation of the bearings, and in particular the design forces on the bearings, right? So this is one issue that comes up specifically in seismic shaking, that the classical method of designing bearings, equally shared and so on, will not work here, because the restrained bearing will take the cake. Now, we also need to understand the concept of bridge vibration units. And the bridge vibration unit here means out of all the pieces that are there in a bridge, the 5 pieces, which are the ones that will oscillate together. And here is one cartoon in which we can see that in the transverse direction, both the substructures, the foundation, the substructure, the bearing and the soil and the superstructure, all of them will act together in the transverse direction. But if you look at in the longitudinal direction, only one side set will act together. And this is very important to understand where will the inertia force get transferred. In fact, as a designer, you will have the freedom to decide where the inertia force should get transferred. It's not like a black box computer program these days. Our students tell us, sir, this is the correct answer. Computer gave this answer. That is not what we want to accept as designers. Designers can tune the behavior of the bridge the way they want the bridge to act under strong seismic shaking. Meaning where the inertia force should go will be determined by the designer. So the choice of the bridge vibration unit will be that of the designer, especially in multi-span bridges. One other important point that one needs to keep in mind that in case of buildings, if you remember seismic design, T is equal to 0.09 h by square root of d, an empirical expression, or T is equal to 0.075 h to the power of 0.75, and so on. These are empirical expressions based on actual measurements made on built buildings. Such an exercise has not been done for bridges, and so we don't have an empirical expression for natural period, fundamental natural period of a bridge. And hence, the entire responsibility of estimating fundamental natural period of a bridge goes to the bridge designer, and the bridge designer has to model all 5 components of the bridge, which is superstructure, bearing, substructure, foundation, as well as soil. I'm saying soil once more. I insist that soil should be modeled because the flexibility of the bridge will depend on the flexibility of the soil. And if you don't account for the flexibility of the soil, you will have great embarrassments in the displacements that will get accrued, especially at the bearings, and we may have unseating or dislodging of bearings. So if one lesson you have to learn from seismic design of bridges, you learn the first one, which is that vertical member will see the damage. The second one is you have to model soil and all the components of the bridge and do a free vibration analysis and obtain the natural period from there. That is what you will see as your primary responsibility. Now you might say, no, you are not telling the whole story. This code has given T is equal to an expression of 2 square root of d by 1000 or 1000 f, right? Yes, that code has given. That is an equivalent static way of trying to estimate the natural period, of estimating the lateral stiffness of the bridge. But even for that, you will have to do the full modeling. The full flexibility of the bridge has to be modeled. Another important area which is often neglected by designers is the matter of slender versus squat members. Many a time we use stick model and we forget to switch on the shear deformation parameter. And I pray that you understand what is the difference between shear deformation and flexure deformation. And if you really bring in the shear deformation parameter, which is the ratio of the lateral translation stiffness and bending versus lateral translation stiffness and shear, you will notice that your 4224 classical matrix will not stand waters, and it can be a radically different number, and so the bending moment values and shear force values will be radically different. So you have to switch on the shear deformation parameter, otherwise you are not making a good estimate of the effects of the actual behavioral characteristics of the members. Just to give you a quick example, the beta factor for a slender RC pier will be 0.01, while that for a wall system will be about a 1.5, which means that in your previous expression, you can see beta very close to 0 has no effect. It will be 4224. But if you can put 1.5 for beta, then numbers will go out of control. And that is exactly what you're seeing. The off diagonal term becomes close to 0. that means you're getting a uncoupling of the rotations in the two. That means the structure is going more towards the shear behavior of the RC pier. So there is a need to understand how many nodes you will model, and especially when you have geometries that are exotic, you will get into great headaches of trying to idealize each of the slices, and you cannot make too small a slice and you can't make too big a slice either, and that is why you have to be very careful. Coming to the issue of bearings, you will now, from use of manufacturer specifications, arrive at what is the vertical compression stiffness, the lateral translational shear stiffness, and the rotational stiffness of the bearing along both the axes of bending in plan, the X and the Y. And then you will put that as an input into your computer analysis. And it is time for us to recognize that most bearings, which were classical type, the traditional ones, rocker roller, you got away by saying that they were rigid bearings. But now, if you're using neoprene or elastomeric bearings with steel reinforcement or and with this lead plug, then the flexibility is high. But the more modern ones, which are the free guided and restrained, again, that flexibility is not available in all directions. So you have to watch out what is that flexibility that is available and model it accordingly. Another issue is that the bearing flexibility will have an impact on the stiffness of the bridge. You can imagine if the bearing was not flexible, you will get 3 EI by L cube. But if the bearing is flexible, you will see much less than that will be the stiffness. And so mere assumptions of the classical understanding will not help us. And now add salt to injury here. Instead of making it a slender pier, if you make it a squat wall, then it will not even be 3I by L cube. It will have now that beta factor, and you have to play with the beta factor to get your quantities in place. So this difference has to be accommodated in the whole process. Now, many a time, designers, for the want of time, get into a large number of assumptions, and the assumptions can be expensive. The bridge with well foundations can be modeled by the last case, as you can see, where you forget completely about the soil and the foundation, and just top of the pier, top of the well is where you start your model. The second case is from where the soil is in contact with the well, there you put equivalent springs, right? And the third case is that you model all of them completely. And the first one should not be used. The second one can be used only when your foundation is very rigid. So if you're having well foundation, that's not on. Only in the case of, in the case of pile foundation, it's not on. In the case of well foundation, definitely this is a possibility for you. But you will, in the early years of your life, be benefited by modeling both the full model as well as the lump soil model, and see what are the differences for different parametric changes, especially soil properties and the aspect ratio of the well. So I would say I'll put my vote for the full model in all cases, and the lumped soil model for limited number of cases. And you will really get lucky if you can get correct numbers with this, but I don't want to live this luck, especially when somebody's life is at stake. I don't want to play with luck. I want to play with facts and not opinions. So while most structures will require this 5 virtues to be followed: safety, functionality, sustainability, aesthetics, and economy, bridge is no exception, and it will also follow the same. The only catch is that if you are able to pay a little more, you can make it look more beautiful. That is the only catch. But in the order safety, functionality, sustainability, those will remain. One aspect that a lot of people think that it is a different subject, and that is called stability. And they think that stability is different from these 5 items and try to list it separately. Stability is part of safety. You cannot design an unstable structure. So first you have to make it stable and design it. After you've designed it, it has to remain stable under rain and shine. What it means is under strong earthquake shaking, it should be able to withstand the damage and still be stable. And that is why stability is looked at in three parts. One is equilibrium stability when you get started, then the geometric stability when you are looking at the slender members and you're taking undue chances, 4-level interchange in a metro city. You're taking chances by being miserly about the vertical member size, then you'll pay the price of geometric nonlinearity coming into picture. And of course, whatever you do under strong shaking, plastic stability is something that you will have to work with and ensure that the collapse mechanism is actually acceptable. Over 130,000 masonry arch bridges of 100 years plus age are waiting for us to help them. And you can understand that arches are not your best friends under seismic shaking. And so we will have to do a strong retrofit game. So those of you who are in the business of looking for a career in bridge engineering, but a solid one, work with Indian Railways and fix their 130,000 bridges. Each one will take you about a year, which means you will live 130,000 years. If you do it alone, if you join with a few friends, you divide 130,000 by NF, number of friends, and that many years you live happily ever after. Okay. One of the major issues that came during the 2001 earthquake is the subject of lateral restrainer stoppers for bridges. These are the most, I would say the smallest of the items in the whole bridge, which costs very little, maybe 5,000 rupees. And that can save the bridge from large embarrassments. In fact, this bridge earlier at the design stage did not have the lateral restrainer, and the peer reviewer had insisted on the lateral restrainer. It was provided, and as a consequence, when the bridge jumped laterally and vertically, this spans did not get dislodged from the pier, and that is a very, very major gain for the transportation system, because the one span that was unfinished, they quickly put that together and they could provide this as the main artery for travel when the parallel adjoining bridge did not function during the earthquake, after the earthquake. Another issue that we are noticing every time is that designers tend to have typical spans, and then the last small change is a short span at the end. And this leads to the depth of the girder being different. As a consequence, the bed block heights are different. And for longitudinal shaking, the bed block of the smaller span gets a beating from the main span of the larger span, main girder of the larger span. And this is a very, very avoidable mistake. And I would urge designers to adjust the small change in the main span itself and make that 4 or 5 spans have a little extra meter length, and make sure that you don't provide such shorter spans. Every time there was a longer span, or every time there was one short span or two short spans, there was trouble at the interface between the two. I don't want to show a large number of earthquake damage pictures here today, but I want to push the concept in so that you'll understand that this is not an acceptable strategy. So when you talk about seismic design, the first item is called configuration. Configuration is bridge configuration. In this case, bridge structural configuration, bridge structural seismic configuration. And the first requirement I will say for bridges is that your stiffnesses of the vertical elements are all the same, including soil stiffness, and in the span lengths are all about the same, and the span weights and masses are also about the same. Only then you will see all spans oscillating nicely back and forth in the transverse direction, and will not have this headache of differential bed block heights. Another practice that has to be discontinued urgently in this country is the use of elastomeric bearings without the end plates. Right? We have done about 4 or 5 decades of this. Let's just plug out of this. This is not acceptable in seismic design. Right? If you want to put a bed block, put a recess in that and throw the pad in there, and at the soffit of the superstructure girder, you want to make an undercut there, and then just try to adjust the two one on top of each other. That was old day bridge engineering. The modern bridge engineering does not allow such laziness in the process, especially for bridges in high seismic regions. So the catch is simple. Large number of people in India have said None of our bridges got damaged. Yes, answer is very simple, because we never connected our bearings. And we got lucky that most of the bridges were not shaken. Once our bridges get shaken and they start dislodging, you will see that this is not an acceptable solution. Now you might say, once I connect the bearings to the superstructure and substructure, where will the damage be? It will go down to the substructure. So as we are speaking, 99% of our bridges do not have lateral restrainers and do not have the elastomeric bearings connected to the superstructure and the substructure. So seismic design, the need is very clear. We are having 57% of land area under seismic zones 3, 4, and 5, which is moderate to severe shaking, and 80% of our population is there. So there is no way you can shy away from doing seismic design. So what is desirable for us on the location of damage is it must be ductile, it must be flexural, and it can be only flexural. Shear is not necessarily, relatively speaking, not necessarily as ductile as flexural. So that will be our best choice. But ductile flexural hinged beam ends, we just said for superstructure we can't have it. So the first option is gone. Second option is ductile action in wall piers, column piers, and piles. We don't want damage in the foundation because we can't even see that our foundations are damaged. So that is also gone for us. So in case of bridges, you will see piers and piers is the only location, wall piers or column piers, where we will be able to see damage in them. But we are looking at building design, then you will say it is undesirable to have any damage in the columns. And of course, nothing in the foundation and soil. So this demarcation, this difference, I want you to learn that in the case of bridges, the piers are the ones that we will want the damage to be concentrated. Now, here again, we have choices to make. We are now heading to a regime where 99% of our new bridges will be single column bridge pier. And it is very scary and very, very fearsome for me when I look at all eggs in one basket. It is like going to Bombay, putting your money in your wallet and putting the wallet in your back pocket, and back pocket doesn't even have a button. Not that the button will save you, but I'm saying you won't even have the sense that something is going away. That is exactly the left option. And the right option is what we have to negotiate, and we have to build more in time ahead. So our choices are between a twin column, twin pier frame pier or a wall pier. Just to show you that we don't need earthquake shaking, even otherwise the substructures are not being attended to carefully, and so we are having damages and collapses in bridges, right? So this is something that I want you to remember, that we have not been paying attention to the bridge design, especially the vertical member. The horizontal is not at all in any trouble. You can see this. I've spick and span. It's so stiff, nothing can happen to it. So of these three options, these are the three practical options that are being implemented these days across the country. But for me, the winner is the Eiffel Tower. The shape of the Eiffel Tower is the best for seismic design of the bridge substructures. Why do I say that? Two reasons. One, I get large lever arm at the base, so overturning is lesser. Second, compression and tension are different segments altogether. So I'll get a whole area for compression and the other side whole area for tension and vice versa. So I get very good behavior in terms of design of individual members here as far as the A-frame legs are concerned, right? So if I were to choose an A-frame, we'll get an A grade for us. So the bridge substructures have two functions. Of course, they have to transfer loads from superstructure to foundation, but also hold up the entire bridge under extreme inelastic conditions, right? And these days we are getting into precast also. So we have to be very, very careful exactly what we are doing. But in either case, the game is that you want to see that the damage is concentrated in the vertical member. You must have seen that under seismic shaking, the bending moments will switch back and forth, and you will see tension side becoming compression side. So how do we really focus this entire seismic behavior into the design of bridges. The one thing that you must remember is earthquake shaking is a displacement under the bridge, and hence it is going to be displacement loading on the bridge. And in colleges, we teach only force loading, which means if displacement is applied at the base, how do we do equivalent analysis and make sure that the bridge has so much displacement capacity also. Four things that you have to do. First, you have to remember that steel and concrete are being put together. They have differential ductility. One has 300, another has 3. So material, we have no choice. This is arranged marriage for us. Next, we come to section. This is where the game is. You have a choice to design the section carefully, and a little later I'll talk about how to make sure that you do all the right things. And the ductility here comes down to 30. From 3 to 300, 3 and 300 together, it will give you a section ductility of 30. But if I put that in a member, the member ductility comes down to 10 as far as curvature is concerned. And then if I put the whole bridge together, I'm getting a displacement ductility of 3. So the thumb rule is the weakest in the chain will win the game. The weakest is concrete. Between steel and concrete, concrete says 3 is the ductility, steel says 300, and in quick time you'll realize that the bridge will have a ductility of 3. Anybody who thought that the bridge will have large lateral ductility is mistaken. So the game is not to make it go below 3. If you just sleep and don't attend to the drawings and sign the drawings, you will make 1 as ductility. Right? If you do bachelor's degree, 1.1. If you do master's degree, 1.5. If you do little more study after that and you have 25 years of experience, you will get to 3. So seismic design of bridges is for the brave and not for the weak-hearted. So don't attempt to design bridges unnecessarily at the starting of your career. Apprentice with a senior engineer, work with that senior engineers and learn the whole set of nuances in the seismic design of bridges. So deformation capacity is the focus for the vertical member. The pier is going to be swung back and forth, and we have to make sure that it has sufficient deformation capacity. One of the key factors of increasing ductility is actually confinement. The unconfined concrete has a ductility of 3. In fact, ductility of 3 only for grade 20, M20, M25, M30. If you're going to M100, the ductility is 1. Right? The new IS 456 will tell you that there is no ductility in M100, and above 60 there is very little ductility, 1.2, 1.3, that kind of numbers. So higher grade concretes are not your friends if you're doing seismic design of bridges. Still lower grades are your friends. And you need to, of course, put this transverse reinforcement close to each other so that the strut action that is getting developed becomes more dense, and only in closed ties you will see a complete core participating. If you have far separated ties, the core completely will not participate. And nothing to talk about an extra other than what we do in buildings. 135-degree hooks are mandatory for us here also. The game changes in the spacing of this reinforcement, and that is where I will draw your attention. Normally in buildings you want damage in the columns, and so in the beams, and then so you say I want hinges at the end, so I'll do a close spacing at the end so that I'll get good confinement there. Very good. You say sometimes no, even building columns also will swing back and forth because I have done a bad design, and the hinges will form in the columns because I made conjuicy. I took 230 mm columns, so columns also will form hinges. If you take healthy columns, this will not happen. But there also the plastic hinges, because it is displacement loading and the upper limit of displacement is not necessarily known to us, we can have a surprise earthquake with a larger displacement. We will say we will also design for plastic hinges at the ends of the columns. Fair enough. Then you put closely spaced at the top and bottom of the column. Very good. Now let's come to the case of a pile foundation in a bridge. Where will you do the detail? How will you do the detailing? Will you say that the plastic hinge is forming, let us say at the depth of fixity, and I will put close spacing there only? Or will you do close spacing and no close spacing below that, and then no close spacing above that? The answer is, at the beginning of shaking, you will see that the shear force is this like a cantilever. The shear force is constant all through, right? At the beginning of shaking, the hinge can get formed at the support here, and as the shaking becomes stronger, the soil can get separated. But if the soil is caving in, you're in trouble again. So you are going to see that the best option for you is, because you don't know that this, first of all, there is covering, which can be 20 meters. Secondly, there is also the issue of loss of contact, which can be 5-10 meters. So in a 40-50 meter pile length, you can lose 30 meters just like that on the basics itself, which means that you don't have the luxury of doing selective detailing. You have to do uniform close spacing throughout the height of the pile. That is the first lesson that we are learning from this today. I'll come to the substructure in a moment. The section ductility, of course, you're looking at non-ductile sections, so you'll get much more brittle. And compare it with the case of steel structures. We just heard Professor Arul Jayachandran. In steel structures, we have a huge set of sections, and they're classified for you. But that's not the luxury in the case of concrete sections. So you have to be very careful in concrete. If you are not able to capture that it's a slender section, you can even cause trouble to yourself. One of the things is that if you have large diameter bars and poor grade of concrete or heavy corrosion, then you will notice that fatigue will become an issue for us, and we will lose ductility because the bond is going to get deteriorated quickly over time, right? And this is a matter that we want to ensure that fatigue is not an issue in the steel structures from the point of a bond slip, but it's an issue in terms of the welding part of it. So the key factor that you're learning now on this picture is that if you put very heavy loads on a column, then you will get very brittle behavior, and lighter loads will give you ductile behavior. And then you might say, what is the meaning of heavy load? Load is always fixed. Yes. If you choose a silly size column, very small patla wala column, the ratio of the maximum capacity to the applied axial load, if that ratio is very large, close to 1, you are in trouble. In your PM interaction diagram, if you're in the top apex of the PM interaction diagram, you're in trouble. So the thumb rule again is healthy column sizes. No slender column sizes, but healthy column sizes will give you good structure ductility. So let's get to ductile design. You have heard about the chain analogy. And so the strength of the chain is the strength of the weakest link. Ductility of the chain is the ductility of the weakest link. Stiffness of the chain is the stiffness of the weakest link. All of them are of the weakest link. So which is the weak link for us? In this case, the weak link is your substructure. So the stiffness of the substructure, stiffness of the strength of the substructure, and ductility of the substructure will govern largely the stiffness, strength, and ductility of the whole bridge. That is where we have to spend a lot of attention in the design and detailing of these bridges. So if the weakest link is strong and brittle, the final answer is going to be governed by the weak link. If the weakest link is strong, if the brittle item is strong, then the weak item is going to decide the behavior. If the brittle item is weak and the strong item is ductile, then you will see that the brittle item will govern. So here is where the judicion is, that we don't want to make our substructure brittle. We want to make it ductile. So there is a hierarchy within the member, and there's a hierarchy between the members for designing them. So as in the case of bridge, the horizontal member, in case of buildings, the beam has to fail before the column. But in the case of bridge, that cannot happen. The column will fail, the vertical member has to fail. There we had an issue of joint. Here we have an issue of bearing. Now, you might say, what's the difference between the bearing and the substructure? There is a concept that the fellow who's transferring forces from one member to another member, that person has to be very, very strong and cannot see any damage. Otherwise, the flow of forces will not be sincere, will not be honest, and will not be accurate. And that is why bearings will still have to be rated for a higher load capacity than the substructure. You might also remember from the design of bearings where the reduction factor is 1 or even 0.8 sometimes, you will see that you're designing for 25% more force because you don't want the bearings to get into any damage. So ductility plays a vital role in determining the deformability of the structure, and we have to do all the good things to make sure ductility comes in. So we have to avoid geometric nonlinearities and bring material nonlinearities into picture. Once the ductile materials get into nonlinear action is when you will get into good behavior. So the step 1 is to choose good configuration. Step 2 is to assess the strength required on the structure from the standard, of course. And the step 3 is to apply safety factors and design all the horizontal members. And then the step 4 will be the issue of collapse mechanism, right? You have to make sure that you know the relative strengths of the members, horizontal and vertical members, and make sure your horizontal member in this case is not damageable, and so the vertical member will see the damage. So you will see if you have a two-story bridge system, you will see this column mechanism here. But it will be possible, if it is possible, that you can put this hinge in the beam segment. You may have a girder here which is very deep and stiff, but if you can make the bridge a little wider and put a beam section here and make sure that the plastic hinge happens in that beam, then you will be able to save the column from getting into shear behavior. Of course, there is a ductile hinge at the bottom here that will be necessary to make the collapse mechanism happen. So our hierarchy here is substructure. First will get damaged, bearing will be the second, superstructure third, foundation fourth, and soil is the fifth, right? And if you're looking at reinforced concrete, you're looking at under reinforced failure. So let me spend a little more time on under reinforced failure. So step 4 is predetermine overall collapse mechanism, and step 5 assess the upper bound of all the ductile elements because you know your predetermined collapse mechanism, and then come up with all the design strategies as given in the standard for the brittle elements. Very good. Now we are saying enhance the ductility of these vertical members. How do we do that is where we are getting into a discussion. One item that you're looking at is that lapping is gone. That is not an acceptable solution for seismic design of bridges. Longitudinal members in a substructure cannot be lapped, cannot be relied upon with just lapping. And so is the story with transverse reinforcement. Lapping is not acceptable. I urge all of you to go back and look at your past drawings, and you will notice that that was one of the ways we were letting it go, but that is not acceptable anymore. Time has come for us to move to more formal methods of fastening the two bars, and coupler will be one of the important points. What we're seeing here is that the current design method for us is that we are doing the forward loop, but we don't know what our bridge is going to do exactly during earthquakes. And this is where a good bridge designer in the country will do the actual behavior, will estimate the actual behavior, and then close the loop and see whether that's an acceptable design, and only then sign the drawings. You can do the forward loop and say I have a code compliant design. That's not acceptable. Code tells you the minimum of everything. Code doesn't say that if you do all these minima that you will get to a good behavior. It doesn't say that. It says that if you do all these minima, it will be better than without following all these minima. And so it is time for us to do a nonlinear analysis of the bridges. So another skill that you have to pick up if you are going to be a bridge designer for the future, whether you're doing new bridges or you're doing retrofit of existing bridges, for both cases, nonlinear analysis will be your good friend. Without nonlinear analysis, don't graduate from colleges, those students who are sitting here. And if you don't know nonlinear analysis, don't take your degree until you learn nonlinear analysis from that university. Make sure that you are able to learn all of it. So the load combinations, there are so many load combinations for us, and they are listed in the standard. All of that apart, you still have to do one more combination, which is related to the overstrength option. And this is how you will save your bridge. So the classical load combinations will not save you because those are all force related, and the displacement related story is coming in the overstrength load combination, which is specified nowadays by the bridge codes explicitly. So let's talk about a little bit about detailing. Any lecture on seismic design of bridges is incomplete without showing you this picture of the collapse of the Hanshin Expressway in Japan. When that single column bridge piers, all eggs in one basket, your purse is in the back pocket of a Bombay local train. That concept was understood very deeply by this great loss that the nation went through. Right? Can't have kilometers length of the bridge just falling off laterally because of lack of strong conceptual basis in the design of bridges. Of course, the method of design changed after this earthquake, but still, if we can learn from them and not repeat their mistakes in our country, we don't have to discover all the mistakes, right? If you don't learn from their mistakes, you are doing blunders, and that is what will be our barometer, that if we haven't learned from other people's mistakes, we are not going to be considered to be a good citizen. So what is the story here? What happened to this Hanshin Expressway that led to this? Many reasons, and we will talk about one at a time. First of all, you're looking at a PM interaction diagram, and you are looking at two cases. In the case of concrete structures, we have an unsymmetric PM interaction diagram, and which says that when you apply a little axial load and compression, you will increase the moment capacity and then it will drop. Many of us know this concept, that we go to a balance point and then we are above the balance point is all compression failure, and below the balance point is all tension failure. And tension failure is desirable because, as you can see here, that when the axial load is small, we get the largest ductility, curvature ductility on the left hand side diagram. In the case of steel structures, of course, you have a symmetric PM interaction diagram, but let's look at concrete here. This is the picture that is familiar to much of more of our senior designers who have seen this book from 1978 or 1980. And this is a PM interaction diagram. And we use this chart very liberally in many of our activities. So we have a green line here, and the green line says above the green line is all compression failure, which means brittle failure. Concrete will crash. And below the green line is where the ductile actions are. That means steel will fail. So if you really want seismic design of bridges, you should not be designing above the green line. In fact, as a compromise, the international standards have asked for 30% of the peak value with no bending moment. You get the pure axial capacity. 30% of that should not be exceeded. So if you're looking at the, let us say, the right hand side diagram, you have 1.3 here. 30% of 1.3 is 0.4. That means somewhere here is where you should be, and you can see here this is 0.8 FYD. That means concrete will still crush, but they gave us some amount of leeway here. That was a compromise number, right? Now, if truly you want to make ductile piers and bridges to swing back and forth with yielding of steel, you should stay below the green line. But where are we today? We are sitting on the apex corner here. We're making very small column sizes, and that is why we are going to have great trouble in the design of bridge piers, because we are making them fail in a brittle manner, because we have chosen very small cross-section area. The new headache that we have bought these days is larger strength. Once you say larger strength, the area is even smaller for us. And so it gets more embarrassing from many other points of view. Now you can look at all the different cover ratios, and you will see that the green line is going to go dip deeper and deeper if the cover becomes larger and larger. So very little operational space is available for us in the case of um, um, ductile bridges. Now watch this one here. This is higher grade steel, 500, right? Earlier, in the case of 415, we had the ratio of 0.15 to 0.1 here. And let's look at it here. It's starting with 0.14 or so and going below 1 here. And as you keep increasing the cover ratio, this gets smaller and smaller and it crosses over to the bottom side. That means higher grade steel is not actually helping you at all in trying to make ductile structures, right? And so when you look at different cases, you will realize that your bridges are going to be getting into a very, very, very brittle behavior if you're not very careful about choosing your design forces and making sure that you have your ductile actions in place. Let's look at this little more on the circular column. Circular column is very popular in the country. In fact, circle is the worst cross section that should be used in structural engineering. Why? Because much of its moment of mass moment of inertia is sitting at the axis. And so for bending, it's the most inefficient section. The topmost fiber reaches the extreme stress. The section has reached the extreme stress. This is the most inefficient section. So my first request when you're choosing a cross-sectional shape is don't choose circle anymore in this country. Make it square if you can and slightly marginally rectangular. 0.4 or a ratio of about 0.8 or so is really good if you're making a column pier. If you make a wall pier, of course, the ratio will be different. But for a column pier, no circles at all, please. Look at this, how this green line is dipping down. And there is very little oxygen left for the green line. You can see here that if you have small cover, that means the column size is very large. Then you are having at least a reasonable, but still it is the axial ratio is 0.1 FCKVD square. Very small. And so this is something that you want to learn just to convince you that we need the axial force to be very small. I'm showing you the moment curvature relation along this entire perimeter of the PM interaction diagram. And in the lower part, you will see that good ductile actions. But as you come above this point here, there's complete brittle action. Your column will never behave in a ductile way. And so please ensure that you're using larger size column, lower grade of concrete, lower grade of steel as the basis in high seismic regions. Elsewhere, I will not compete, but if you are doing confinement, you will see that this there'll be a little rise in the behavior of these concretes in higher compression region, but the ductility is not much of a gain. The main ductility lies only in the lower axial load ratio, and that is where much of the ductile behavior is. So confining is essential for us, and choosing the correct cross section, correct grade of steel, and correct grade of concrete. The good news is that there is one interaction that we are not doing so far, which is PVM interaction diagram. We are forgetting V and we're doing independently V. In time to come, the heat will be on and we will do PVM interaction diagram for concretes also. And there you will see more trouble coming into picture, right? So axial loads, as I said, are painful for us. You can see this for vertical shaking. There's a elephant foot buckling of the reinforcement between the stirrups, transverse stirrups that are there. So we are looking at the ratio, the spacing of these stirrups to be much more stringent than what we would do normally. And the other issue that we are seeing is that you have large number of cross sections being suggested in practice, and some of the cross sections we have to stop urgently. And as you can see on this, we have counted off 4 of them, and only I pray that the remaining 4 you can use. Of course, in the solid, we would still recommend a rectangular, and you can use a solid hollow also, but never a circular one, always a rectangular one. And that is why whenever I see a picture like this, I feel heartening. It's heartening to see a square, near square cross section being used. One issue that is coming up in wall piers is the shear failure. It has to fail in shear only, the wall pier. But then the question is, how do you really make it fail in shear? Now, for a substructure, one of the issues that I'm talking about now is the transverse reinforcement. So when you do seismic design for, let's say, shaking in the horizontal direction, you are going to put the number of legs that you put will give you benefit for the confining action. Very good. And likewise in the other direction also. But if you have opening, then you have to move some of this steel to the outside outside the opening area and make sure this additional steel is able to capture the same amount of reinforcement. In a hollow section, of course, you will see that the crack will cross at different locations and the spacing has to be more uniform throughout the section. One of the things that I want to talk about here is that we talk about all these detailing requirements and then we use these column sizes. The pier sizes are also in meters. And when you get bar diameter, bar lengths which are very small, you are forced to use couplers. If you don't use couplers, you don't get the advantage of that. So let me talk about the use of couplers. First of all, in longitudinal bars, splicing is not acceptable for us. Welding is not acceptable for us in seismic design. And the only thing that is acceptable for us is couplers, right? Splicing, because there is no guarantee of a bond transfer between the two under cyclic loading that earthquake shaking will do. Welding, because welding causes large reduction in the strength of the steel bar in the neighborhood of the weld area. And hence welding is not acceptable. The only thing that you can take is the mechanical couplers. Now let's talk about transverse reinforcement. You saw the Hanshin Expressway failure. The Hanshin Expressway failure was having transverse reinforcement like this. And as a consequence, when the shaking happens, compression force comes from the top. The concrete wants to dilate in the horizontal direction and the splicing is not going to stop it. So transverse reinforcement is going to give way. Welding is not acceptable for the same reason that it reduces the strength of the steel bar. So again, you need couplers here. Of course, there's a possibility of anchorage in the case of transverse reinforcement. If you can bend it into the body of the concrete, nothing like it, then you can avoid the use of couplers also. So we started with this issue of wall aspect ratio, and it has to fail in shear. That is where the game is, that when you're talking about squat walls, how do you really make them fail in shear? The important part in squat walls is that the vertical reinforcement has to be larger than the horizontal reinforcement. This is the opposite of what will happen in a slender wall, where the vertical reinforcement has to be less than the horizontal reinforcement. In the slender wall or in a column pier, the plastic hinge has to happen, so the longitudinal bar has to yield. That is why longitudinal reinforcement has to be lesser. In this case, the shear crack will pass through and the bridge has to swing horizontally to get ductile action, move horizontally to get ductile action. And that can happen only if the horizontal reinforcement is lesser than the vertical reinforcement. One of the issues that I want to drive home today is the fact that different grades of steel will have the same modulus, elastic modulus. So let's look at choosing the grades correctly, transverse bars and longitudinal. What should be the grades? So especially for transverse reinforcement, that's the vertical bars. Those are the transverse reinforcements, and then there is a certain spacing that you're looking at. And under the action of vertical compression, this transverse reinforcement will go stretch outwards, and hence as a consequence you can look at it as springs, and therefore the EA by L of the transverse reinforcement comes into picture. EA by L is axial stiffness of the transverse reinforcement. Irrespective of grade of concrete, E is same. That means if you use higher grade concrete, you're reducing state. and as a consequence, your EAI by L is lesser. So higher grade concrete will give you lesser confinement, higher grade steel will give you lesser confining action. And so for transverse reinforcement, the higher grade of steel is not acceptable. Okay. And that is where we are talking about transverse reinforcement to be necessarily when kept at 415. You can use 550, but in calculation, you will use 415 only. If you're not having the availability of lower grades, you can use higher grade, but please make sure that your calculations are done with 415. This is what the clauses are also saying. Higher grade will give you smaller A, which is not acceptable, right? And so this is an important point which will come into picture when we decide the spacing of transverse reinforcement also. And please ensure that you recognize the dilation and provide for the lower grade of steel, or use lower grade steel FY for the purpose of estimating the transverse reinforcement. So transverse bars have to be 415, at least in calculation, if not in practice. Longitudinal should be same grade as transverse. If not, it can be a little higher, but too high is also not good, because we showed you on PM interaction diagram, we will not be winning at all. I'll stop here by saying in time ahead, you will have to learn some more new things. That bridges will come under a different category of structures, and that you will need to design for 3 levels of earthquake shaking. And the design will be done for severe, but you'll have to do a check for at the serviceability level and a check at the integrity level under extreme shaking. The first one will be limit state method, the next one is working stress method, and the last one is nonlinear analysis method, right? Which means that we have to change our tool set that we carry forward in time ahead. And as I said, we need to do the closed loop design. This is what we will have to do in time ahead. So the design expectations from us are increasing slowly over time, and we should be able to meet that very, very robustly. As of now, we are in the early stages of the design. We should raise our understanding, and I pray that we will be able to come up with better and better bridges with higher performance in the time ahead. And just to put everything in perspective, the new IS 456 is asking us to do 6 things. And in bridges also, you will be doing integrity check, which is nonlinear analysis based. And that is why I'm warning us, all the colleagues here, that it's time to improve the skill set in the road ahead. So for earthquake resistant design, displacement will become a focus for us, and piers will take most of our attention, and pile foundations and flexible soils will require extra attention from us, because they are going to swing back and forth, and we need to understand their behavior.
The importance and purpose of foundation. All structures, including bridges, require a system called foundation to transmit all the loads from the structure safely to underlying soil or rock in the earth. It is evident from the above definition that foundation is the most important part of the bridge. The foundations may be classified based on where the load is transmitted to the ground as shallow foundations. The shallow foundations consist of open foundations. Some examples of open foundations are isolated footings, combined footing, raft foundation, etc. Then we have a shaft foundations are also nowadays we are using. Shaft foundations are used to support lightly loaded structures like compound walls, supports for electrical poles, highway signage boards, etc. They are designed as short piles, taking into consideration of the passive pressure mobilized with a mechanism like what is seen here. I think one more thing, how to get the cursor presented. Okay.
Mr. Anjanelu, go to pointer option, and there you can
Pointer
ask
option,
for,
yeah.
yeah, in the pointer option, you can ask for laser or something. Go to pointer option. Yeah, and then you have a laser
Laser.
pointer. Right side you have a laser pointer. Yeah,
Yes.
now you'll get it.
Yeah, yeah. Then we have deep foundations, which deep foundations consist of well foundations, pile foundations, and monopile foundations. The small diagrams are there: well foundation, pile foundation, and monopile foundation. This is the one of the latest things in the market, which I think not much used till now in India. I think, but at the same time, I think it started using. Then the selection of the type of foundation to be adopted in a bridge project is primarily based on the discharge, cover level of the river below the bed level, type of soil available, whether inerodable rock strata is available at a what depth, etc. These are the considerations for selecting the whether to go for deep foundation or shallow foundation. Shallow foundations are adopted in minor rivers, streams where the discharge is small, where inerodable bed is available at short depths like 4 to 5 meters below the bed. In minor bridges, shallow foundations like raft foundations are adopted even if inerodable bed is not available at shallow depths by making the bed inerodable using raft foundations with upstream downstream floor protection using rigid apron curtain walls, flexible aprons, etc. Then for the proper design of a foundations, investigations are required, both hydraulic investigations as well as soil investigations. Hydraulic investigations, the catchment area of a river at a bridge from which rainwater discharged in the stream at the bridge location is determined using topo sheets available with Survey of India. Or nowadays, a lot of softwares are also available to do this. Uh, the design discharge is calculated based on the rainfall intensity in the region, distribution of rainfall in time and space, duration of rainfall, etc. And IRCs, these things are given in IRC 6, depending on the catchment area. For the design of the foundation, we need to increase the discharge by certain percentage, which are given in the code. Then from the design discharge, riverbed slope and cross section, the linear waterway is required is calculated using Lacy's equation. Sometimes it is economical and safe to keep the bridge width less than the required linear waterway. This results in cover in the bed when the bed consists of erodible strata like sand, silts, etc. The highest flood level is calculated for this linear waterway and the covered bed level. And after that, the depth of cover is calculated based on these formulas given in the code. The mean depth of cover below HFL for natural channels, that DSM is equal to that this one. And after this, once we get the cover level, that is then for the maximum depth of cover for foundation design, because of the local cover effects and all these things, the IRC 78 gives you to increase the cover as twice DSM for pier design and 1.257 DSM for abutment design. Then apart from this hydraulic investigation, subsoil investigations are also required to determine for the design of the thing, to determine the characteristics of the existing geomaterial like soil, rock, bed material in watercourse, etc. To determine the type of foundation to be adopted, whether shallow foundation or a deep foundation. In deep foundations, whether to use a well foundation or pile foundation. A number of tests are conducted on the soils and rock to, in the subsoil exploration like SPT test on undisturbed samples and disturbed soils, core recovery, RQD, unconfined UCT of rock, plate load test, etc. After getting all this information, then all this information is used to select the type of foundation. we obtain the following information from the hydraulic data: design high flood level, free board to be adopted based on the design discharge of the river, designs cover level, velocity of the flow, and we obtain the following information from the soil subsoil investigation: depth and type of soil strata, depth at which rock inerodable strata is available, SPC of the soil below the cover level, SPC of the rock. Based on the above information, type of foundation and depth of foundation below bed's cover level is adopted among the following types of foundation: shallow foundation, raft foundations with protection of the bed protection against cover, or individual footings which go below the cover level. Once you for the deep foundation, either well foundation or pile foundation. And criteria for selection of these foundations is raft foundation with bed protection against cover. This type of foundations are adopted in minor bridges with raft foundation just below the bed level. Foundation is protected against covering action using appropriately designed upstream downstream aprons. These are dealt with IRC SP 13. Then individual foundation for pier or abutment. These individual foundations are adopted when soft hard rock is available at shallow depths below river bed level. In case of flyovers and viaducts, when semi-disintegrated rock, soft hard rocks or hard soil strata is available at shallow depth below bed, ground, etc. Well foundations are adopted in the following cases: the river discharge, velocity of flow, and cover levels are very high, as in the case of all the major rivers and plains, where competent foundation strata like rock is available at high depths below the bed, where predominantly cohesionless soil or clay soils are only available at up to very large depths. These are also the places where well foundations are adopted. Well foundations are designed taking advantage of the passive earth pressure that can be developed and which helps in the stability of well foundation against the high water current forces or seismic and wind forces that can develop. But well foundations are not popular nowadays because of the relative lack of control over the progress of well sinking, tilts and shifts that develop during sinking. Typically, correction of well tilt or shift takes well over 3 to 6 months time, and sometimes whole project gets delayed because of the selection of the well foundation. That's why nowadays people are not very enthusiastic to go in for well foundations, especially because pile foundation technology has improved a lot. So pile foundations, there are a lot of varieties of pile foundations like precast driven piles, board cast in situ piles, board cast in situ piles, and board precast piles. Only board cast in situ piles are being adopted for bridges as well as flyovers, viaducts in India for the following reasons. With the advent of high capacity pile boring machines capable of rotary drilling, the speed of construction improves tremendously. These can be adopted in city situations where high width of roads cannot be barricaded for open foundation. In case of open foundation, typically you require a barricading width of about 7 to 8 meters, which are nowadays not possible with the traffic conditions and all. So that is also one of the reasons why pile foundations are preferred. Even in situations of high cover level, where earlier well foundations were being adopted, nowadays they are being pile foundations are being adopted using board piles of 1500 mm or even more nowadays. The concept of monopile is being adopted where it has all the advantages of a well foundation, but without the disadvantages of well foundation like speed of construction, control of tilts and shifts. Monopile foundation is somewhere between pile foundation and well foundation. These are large diameter piles of 2 meters to 2.5 meters in diameter and are constructed similar to board cast in situ piles. These are recent additions to the range of foundations and are made possible owing to the availability of large diameter rotary piling rigs that have come into the market. These monopiles are extensively used in the construction of Dubai Metro project. Then from the foundation, now we come to the substructure. Bridge substructures consist of pier cap, pier, abutment cap, and abutments, along with dirt wall, return wall, etc. A typical thing is shown here, all these components. Then pier caps, which are a part of the substructure, they transmit the loads coming from the bearings and superstructure to the pier. Pier caps are following types. Short width pier caps, which are mainly used for box girder superstructure. The ratio here, the ratio of the depth to outstanding length of the pier cap is usually less than 1. And for that reason, they are designed as corbels. Then a typical corbel is shown here. Then otherwise, RCC hammerhead pier caps, which are used mainly for the girder bridges, where the overhang is more than 2 times the depth of depth of the cap. Then this is a cap is shown here, where for a large width 24-meter wide bridge also, girders are used. In that case, a long cap is you will get. And here you may have to design it as a PSC rather than an RCC cap. Then this is a precast RCC cap that was done for a project in Hyderabad. This is the thing. This cap is cast with a hole here, and after this is placed on the pier, this is concreted and made contiguous. Then the piers, in the pier is the main bending element transmitting the superstructure loads onto the ground through the foundation. Piers of the following type: circular, rectangular. Then these are all for the to reduce the scour action. This kind of shapes are used. Cut waters. And otherwise, wall type of piers. Wall type of pier with a circular, semicircular cut water, and hollow pier and hollow circular piers, and portal piers. Nowadays, these portal piers are also coming to picture because of the large width of the bridges for things like 6-lane bridges, 8-lane bridges are coming. So where used for these portal piers are very useful, and these are very good in the for the seismic transmission of the seismic loads also. Abutments is the end element of the bridge substructure adjoining the approach filling. They are of the following types: cantilever abutment, counterfort abutment, box type abutment where it also acts as return wall, pier type abutment used in flyovers with RE wall behind. So these are all a typical pier type abutment with RE wall behind is like this. And then this is a counterfort abutment where there is a vertical wall with a number of counterforts. See this, the plan of that counterfort is this. This is that wall, and these are a number of counterforts. And even the return wall also has got counterforts. These are when the abutment is very tall, you typically go for this kind of arrangement, where even return walls are also made with counterforts. Then this is a box type of abutment. Simply you make box and keep filling it up, and this thing. And here, this is the abutment wall where the superstructure loads are coming, and this will act as a return wall also. The whole thing is a box with maybe a number of compartments like that. The design of bridge, now that was just an arrangement of how general arrangement things were shown. Now we come to the design of the bridge foundations. Foundations are required to be designed to transmit all the forces of nature operating on the bridge structure safely to the Earth's data. They are required to be designed for the following loads. Dead loads comprising of self-weight of the various bridge components like superstructure, substructure, and foundation. Superimposed dead loads like wearing cord, railing, crash barrier, curbs, utility lines like water pipelines, power cables, etc. Live loads like vehicle loads, pedestrian loads, along with the associated horizontal loads like braking, centrifugal force in case of covered bridges, flyovers, etc. Then water current forces uh, coming from the rivers, buoyancy of the loads due to submergence in water, water of the water, impact of floating debris or vessels, impact of vehicles in the case of flyovers and flyovers viaducts, wind loads on the structure, temperature effect, seismic forces, and pressure including live load surcharge and abutment designs. The, the combination of the above loads along with the specified load factors as specified in IRC 6 to be considered for the design of foundations are: for the verification of equilibrium, the loads and the load factors are given in table B1. For the verification of your strength in ULS, the table B2. Verification of the SLS serviceability, the B3. Checking of base pressure and design of foundations. This is table B4. Then the issues with the pier design. The piers are normally solid rectangular or circular or even annual hollow piers also. In the case of hollow piers, minimum thickness of the wall shall be 300 mm. Wall type of pier in the loads, axial load combined with biaxial bending also is to be treated in the design of the pier. And sometimes very less vertical load becomes more critical when the horizontal forces are very high. Very less vertical load becomes critical in the design. In case of surface recesses, minimum cover is to be maintained. These are, and nowadays it is preferred for the concreting of the pier to be done in one go using tremie pipes like this, what is shown here. The whole thing is done in one go. And if you go for flexible piers, it causes less earthquake forces. Issues related to the pier cap design, normally designed as corbels brackets due to short cantilevers. Long pier cap can be designed as a beam. Longitudinal forces in the bearings, they cause torsion in the pier cap because of the unequal loads and unequal bearing loads. They cause torsion in the pier cap, which is to be accounted. And transverse forces in the bearings, they cause tension in the pier cap, which is also to be, though it is not a very major force, but it is to be accounted for in the design. Then codal provision for the corbels. Corbels may be designed by using strut and tie model, and reinforcement corresponding to the ties designed using strut and tie model should be fully anchored beyond the node under the bearing plate by using U-hoops or anchorage devices such as welding. When corbel with AC is less than 0.5 HC, closed horizontal or inclined links are to be used. In corbels with AC greater than 0.5 HC, closed vertical stirrups with area is to be used along with the horizontal stirrups. Vertical stirrups are also to be used. And these are a typical reinforcement arrangement within the corbels, it is shown. And we will now just give a small design examples which were done in our office in some projects, just to get an idea of what kind of a design things are there. Based on the above principles, a sample design of different types of foundations designed in our office are shown below. Open foundation design on a rocky strata. This is open foundation is done for a project in Hyderabad, because in Hyderabad typically you get rocky strata at very shallow depths below the road. This is this project, a typical four span continuous structure of 30-meter spans are there, and this is a 4-lane flyover with a deck width of 16.6 meters, and it has consisting of 6 numbers of precast pre-tensioned girders and RCC deck slab. Rocky strata is available typically at 2.5 3 meters below the road level, and hence open foundations are adopted. Since foundation strata is raw, foundation is designed for a part of the foundation to lose contact with the foundation strata as specified in clause of this clause so and so of IRC 78. And this is a cross section of the superstructure, and these are the cross section of the pre-tensioned girders. And this is the pier cap. This is a width of 15.6 meter is the pier cap width, and the pier is about 3 meter by 1.5 meter, and open foundations are about 7 meters by 5.5 meters with a depth of 1.8 meter. So here, once analysis is done and we get all the loads, a summary of dead loads and superimposed loads on the pier are shown here, because I have not given all the calculations, only just important things, steps are shown. Yes, here if you see in the service condition, the dead load at the foundation bottom is calculated and at the pier bottom. And this is used for the pier design, and this is used for the foundation design. And then self weight of the soil backfill is calculated, volume of the soil above the footing, and weight of the soil using a density of 18 is taken. And because this is a 4-span continuous structure, there are some secondary loads on the substructure because of the continuity of superstructure, like differential shrinkage, because it's a PSC girder and RCC composite superstructure. There is some loads, vertical loads due to differential shrinkage, which are calculated, and due to temperature rise also what is the effect of the temperature rise on the substructure loads is calculated. Temperature fall, this kind of loads will come. And support settlement. Since we are going for open foundations, we have designed for a support settlement also. Then even dead loads also, there is a vertical load because of the continuity. First, dead loads are the construction stage. First, girders are simply supported, and then later they are made continuous. And because of the shrinkage and the other effects, you will get some vertical loads also, vertical uplift load on the pier. And then even the pre-stressing force, once it becomes, when the structure is made continuous, that also exerts some vertical load. Because of the loss of pre-stress and those things, you get a vertical load. All these things are summarized. That effect also is taken in the design of the substructure and the foundation. With all these things, you get for the live loads also, your vertical loads and horizontal bending moments due to horizontal loads also calculated at the footing bottom as well as the pier bottom. And here, these are the typical cases where maximum vertical load case, minimum vertical load case, maximum transverse moment case, and maximum longitudinal moment case. These are the moment cases, and in each case, what is the vertical load, what is the longitudinal moment, what is the transverse moment, they're all calculated and tabulated. And then wind loads are calculated for the basic wind speed of in Hyderabad of 44 meters. And then this is because the code gives for the 33 meter per second loads. This is calculated, this is converted into 44 meter per second case. And then wind pressure is calculated. And then this is a type of wind lateral loads due to wind on the superstructure, on the cap, on the pier. They are all taken, and their lever arms are also taken, respective lever arms. From that, from the vertical loads, there is a even uplift load due to wind is also considered. And due to the horizontal loads, what are the bending moments, longitudinal moments and transverse moments. From the wind, you get the transverse moments, but 25% of that is taken as a longitudinal moment, as given in the IRC 6. With this, also all the loads are calculated. Loads and bending moments are calculated. And similarly, seismic loads are also calculated. This is a zone 2 with appropriate factors, everything, they are also calculated. And this also seismic coefficient method was used because this is only zone 2. We did not go for any elaborate seismic analysis and all. We have used this seismic coefficient method and calculated the seismic coefficients, transverse coefficient and longitudinal seismic coefficient. And this is, since this is a 4-span continuous structure, the mass of all the 4 spans is considered for calculating the longitudinal seismic coefficient. So you get a seismic coefficient of 0.22 in the longitudinal coefficient, and whereas the transverse you get 0.75. And with this, a summary of seismic loads is shown here with the moments and at the pier footing bottom and the pier bottom. And once this is for the design of the pier foundation. The foundation is a 7 meters by 5.5 meters, whereas the pier is 3 meters in the transverse direction and 1.5 meters along the traffic. Then these are the various load combinations, and for the footing at the bottom of the footing, and the dead loads and soil backfill, SIDL, secondary effects due to pre-stress and this one, and then live loads. In the live loads, maximum vertical load, the live load combination which gives maximum vertical load, maximum transverse moment, maximum longitudinal moment are tabulated here. Then wind load, seismic load. Then section properties of the footing are calculated. Area, ZL, ZT are calculated and check for base. Then this is all these properties, using the properties and the loads, base pressures are calculated. Base pressures are in the 4 corners of the footing, we are getting a maximum pressure of 756 and a minimum of minus 124. That means there is a tension. One corner is losing contact with the earth. This is permitted for the case of when the footings is on a rocky strata, tension is permitted in the code. So that we have utilized that. So with the minimum base pressure of minus and the maximum of this. Hence there is a loss of contact of the footing. Base pressure is redistributed and calculated using this. This is the method used to calculate the tension area and redistribution of maximum pressure. We get ML by P is the EL, and EL by L and ET by B. And from this, uh, there is a method given in the foundation design by WC Tang that is used, that's being used in our office. And here this case falls in case 2. For this, these are the things, those are all given. You can see they're all given case 1, case 2, case 3, case 4, like that. And these are the tables. From this, we have used these tables and these formulae to calculate the tension area as well as. So from using this, we find that 7.7% of the area is going in tension, which is less than 33%, which is allowed in the code. That's it. Then after because this much is the area is losing contact with the soil, the maximum pressure gets enhanced, gets redistributed, which is calculated using that formulas given in there. And we find because of there's a loss of contact to 7.5%, 7.7%, the maximum pressure is becoming 774 against earlier 756. Because there is a loss of contact with the soil, now that is becoming 774, which is less than 1000 kN per square meter, which is allowed on the rock, in the rock of that strata what we have taken. So this is the way a typical foundation sizing is done. Once foundation sizing is done, the structural design of the foundation, for this we have just taken sections like this in the traffic direction and along the traffic direction, across the traffic direction. And then these are all the typical coefficients. Everything is calculated from IRC 112. And this is this one. And summary of moments at the face of the column. In the longitudinal direction, we have got 2000 kN meter per meter, and transverse direction we got 2146 kN meter per meter. From this, width of the structural design is done by taking the design bending moment and then effective width of the section. Actually, the effective width of section is taken like this. This 3200, this I will just show you. Yeah, this one is, if you see, since this is the shape of this is like this. This is 3200. We are the neutral axis is somewhere here. So actually the area in compression is in this shape. In this shape. For this, there is an approximate formula which was used to calculate the effective width of section 3200 plus that extra divided by 8. Instead of 3200, we have taken an average width of 3675. With this, the bending moment is calculated as 23,071, whereas minimum area of steel based on this clause of 112, we require a minimum area of 17,000, and so hence we have got more. We have put more than that, and required is 18,000, and we have used 23,000. Similar exercise is done in the transverse direction also, and we have arrived at this reinforcement of same 37 numbers of torque 25 each direction. Then, apart from this bending moment design, footing is to be checked for shear also. Most of the time, we use the depth of the footing such that it is safe without any shear reinforcement. But sometimes you may require shear reinforcement in the terms of shear stirrups. Usually shear does not govern, as we provide sufficient footing depth to avoid shear stirrups. However, following checks shall be done to satisfy the shear criteria given in the code. Check of one-way shear at D/2 of the face from the face of pier. Check of the punching shear at the face of the pier. This is explained in the following example. But that is then apart from shear, we need to design check SLS. Footing shall be checked for stresses in concrete and steel in rare combination and crack width in quasi-permanent combination. And then I think that those things are we have skipped. Now we go for a design of the pier. So this is a typical, this our pier is 3 meters by 1.5 and height of the pier is 9.5 meters. Then these are the summary of the forces at the bottom of the pier. Bottom of the pier. And then material properties. Load combination. The combination of the above loads along with the specified load factors as specified in table B2 and B3 are used for the ULS and SLS respectively. Then we need to check the slenderness effect in the pier. Slenderness ratio calculation. Height of the pier is 9.453. Effective length of the pier in the longitudinal direction is taken as 1.4 times L. This is given in the IRC 12 because this is a 4-span continuous bridge. This is the factor that is given in the longitudinal direction. In the transverse direction, it is a complete cantilever. So that's why the 2.3 factor is taken. And then radius of gyration, Rxx is 0.433, Ryy is 0.866. Slenderness ratio in X direction is 30.69 and in the Y direction it is 25.21. Both are less than 50, short column. Of course, this is this short column less than 50 is given in the earlier IRC. Now in IRC 112, we need to check for second order effects based on the this clause. And this is done for the slenderness ratio lambda 20 ABC by root n. Here A is depending on the moment in the quasi-permanent moment divided by the first order bending moment in the design load combination ULS combination. So we find this M0 is 11,277 in one direction and 0 in in the longitudinal direction. And in the transverse direction, 309 and 12,969. So we get a factor of 1 and 0.99. Then B, this depends on the percentage of the reinforcement which we used in the pier. So we get a factor of, Then there is another factor N. This is also calculated. This depends on the axial force that is there on the pier against the moments at top and bottom. And then we get an N factor of 0.1918 here. Then with this, the limiting slenderness ratio is 20 into A, B, C divided by this root n. We get a 78.73. This is a limiting factor beyond which actually it is really, you need to take second order effects. This is in the longitudinal direction, we get a coefficient 78.73 and transverse direction 57.23. Whereas actual slenderness that we get is only 30 against allowable 78.73. Hence, second order effect is not necessary to be considered in this. Suppose our pier is only about 9 meters. In fact, some other thing, when the pier height becomes about 15 to 20 meters, we get a second order effects. We get second order effect moments as much as about 30% of the main moments. But here in this case, there are no second order effects. Then we come to the structural design of the pier. SLS check is done for stresses and ULS check is done for moment interaction ratio, capacity ratio. Summary of stresses and moments interaction ratio is given below. Results are extracted from AdSet software of Viasys. We are using this one in our office, but there are so many other softwares also with which you can do that. Then, see, these are the permissible stresses. In SLS, these are the permissible stresses. 0.48 FCK, 0.8 FY. This is, you can go up to 0.8 if you consider fatigue effects. Otherwise, you have to go for only 0.6 FY. So this is a reinforcement that we have provided in that pier. About 0.66% we have provided in the pier. And then check for minimum steel. As per this clause of 112, the minimum steel that is to be provided is 9,000 square mm, and the maximum is 1,80,000. What is provided is somewhere in between, so it is okay. So this is the reinforcement. This is how it is reinforcement is arranged, and then using the AdSec, we get the following results. In one of the cases, the governing case is serial number 32, where there is a PMLMU, whereas MR is 12,006, whereas moment capacity we got for the reinforcement that we have used, it came as 15,000. 15,000. Capacity ratio is 0.8, less than 1. Then hence it is okay in ULS. Then in SLS check, that AdSec gives a stress of 9.56 against allowable compressive stress of 19.2 and tensile stress in steel of only 122 against allowable 400 or 300 as the case may be, whichever way is much less. And since this is a pier with a crack width is not coming, crack width is 0, it is uncracked section. Hence section is safe for the reinforcement that we have provided. This is the typical calculations of the pier design. And these are the typical drawings which we have prepared for this project. And this is the pier reinforcement with horizontal stirrups in different directions that is shown. And then we go to the well foundations. We have designed a well foundation for a river bridge in Assam with simply supported spans of 42.3 meters. Just now, Professor Murthy, as he was telling, that with a high seismic zones, it is better to go for continuous spans. But because of the various constraints of the construction agency, we have used only simply supported spans for this project. Simply supported spans of 42.3 meters with precast post-tension girders and RCC slab. In this bridge location, the strata is sandy up to 40-50 meters below bed level. Hence, well foundation with a 7-meter dia well is adopted under the piers, as well as abutment. Well is designed to take advantage of the passive earth pressure that is developed below the cover level to counter all the horizontal forces, including seismic forces in zone 5, along with the associated hydrodynamic forces. We have calculated we have taken care of the hydrodynamic forces also as specified in the bridge, as specified in the code. This is a worked out example of the well foundation. We have used a 2-meter dia circular pier. The piers are not very tall. We have used a 2-meter dia circular pier. In fact, this is also as Professor Murthy just now told, these are also not a preferred thing, but we have used this. In fact, because we have yet to learn a lot of learning in seismic design. We are that this subject is in still infancy stage. We have to catch up. We have used a circular pier here and 7-meter dia well, and in diameter of the well inner is 4.9, staining thickness of 1.05, and well cap thickness of 2.25. The length of well below well cap top is 23.75 meters, out of which depth of scour is about 9.5 meters, and is below the scour we have gone about 14 meters. Then SBC at that level is 90 tons per square meter, seismic zone 5. So this is the type of arrangement that is done. It's a four girder arrangement. Width of the bridge is about 12 meters and 4 girders, and seismic stoppers are used, both longitudinal as well as transverse direction. And this is the thing. Then type of loads to be considered in the well design. Loads from superstructure, substructure, pier cap, pier, well staining, well cap, sand filling, top and bottom plug, SIDL, very good, buoyancy effect, live load from superstructure and its associated loads, loads due to earth pressure, active and passive, wind loads, and seismic loads in three directions: longitudinal, transverse, vertical, water current forces, and hydrodynamic forces due to seismic hydrodynamic forces. Bridge is designed for two conditions: HFL condition and low water level condition. Because sometimes low water level condition also is checked, because scour level is less in low water condition, hence more seismic forces are attracted. That is also considered, and both designed is HFL condition as well as low water level condition is designed. So a typical of all the calculations, this is what we get for the best seismic case is governing the design, and hence only this case is presented. The loads due to dead load, SIDL, live load, seismic load, water current forces, hydrodynamic forces, we get a P of vertical load of 27,656 kN and moment of 55,313 resulting moment. And then there is a moment due to tilt and shift of well, 8,000 is considered. And against this, there is a passive pressure of 1,60,172 kN meter pressure, which is much higher than the this moment. So all the moments are nullified by the passive earth pressure. Hence, net load at the bottom of the foundation is only a vertical load of 27,656, no moments. And this is the area of cross section of the well, so which gives a base pressure of 719 against allowable 900, enhanced by 25% for the seismic case. So this is how the 7-meter diameter well is sufficient, mainly because of we are able to nullify all the horizontal load effects because of the passive earth pressure. Then the design of steining. Calculation of critical section for steining design. The position of the critical section from the top of the well shall be calculated by equating the horizontal forces, external forces to the passive earth pressure to get zero shear point. Because at the zero shear point, the bending moment in the steining will be the maximum. So we have calculated the location where the bending moment is maximum in the steining. Position of the critical section is force due to passive earth pressure is 265.7 h square. Total external horizontal force is factored horizontal force is 6,244. Design critical section below scour level is HH is equal to square root of this by 265, which comes to 4.85. So hence depth of critical section of section below the well cap level is 45.35, and then we have calculated the bending moment at that location. Force due to passive earth pressure is this, and then total external horizontal force, the same thing is repeated. Sorry. Then the styling, we have used a grade of M35, and steel is Fe 500D, and we have put 106 numbers of 16 mm on each face of the styling. So same using the headset, we get a capacity ratio of 0.95, 0.94 for you in the ULS, which is less than 1. The governing case is seismic transverse case. Then we have checked SLS also. In the SLS, maximum the stresses need not be checked for SLS seismic combination in SLS. So we have only checked the this combination. The maximum stress in concrete comes to 2.5 against allowable 16.8. Minimum stress in concrete minus 0.34. Actually, that means this is the uncracked section. Allowable tension in concrete is minus 1.54, whereas we get only minus 0.34. Hence, is the uncracked section. Then well cap design. The well cap is designed as a circular plate fixed at ends, because standing reinforcement is going into that. The load coming from the pier will act on an effective width of the cap, dispersed width. The bending moment is taken as WL square by 30 for the negative, and WL square by 60 for the bottom reinforcement. For calculating the bottom reinforcement, for the top reinforcement, this one, and bottom reinforcement is done. Then this is a typical how the standing reinforcement is kept, and the well cap reinforcement, and then cutting edge details and all are given here. Then this is the drawing for that. And here, you cannot see this. Okay, it's okay. Actually, just I wanted to show, we have done 2 layers of reinforcement for the pier that I wanted to show. Then this is a for a large cap, the arrangement of the longitudinal reinforcement and stirrups and all are shown in this. Then we will go for a typical pile foundation design. This is we have done this pile foundations in a flyover in Visakhapatnam, simply supported spans of 30 meters. Foundation strata is clayey up to 6 meters, followed by 2 to 3 meters STR, and then soft hard rock below. Board cast in-situ piles foundations are founded in soft hard rock with a socketing of 3D. It's actually not a very hard rock, it's a soft rock, which we could go for a socketing of 3D. 4 numbers of 1200 dia piles are adopted for this, under each pier. And here also we have gone for 2 meter dia circular piers and 1.2 meter dia piles of 4 numbers with a spacing of 4.5 by 4.5. Size of pile cap is 6 meters by 6 meters. Depth of the cap is 1.8. Length of the pile below pile cap is 15 meters. Load carrying capacity, vertical load carrying capacity is 400 tons, and transverse lateral load is capacity is 60. Then this is a typical arrangement, and then this is the properties of the pile. Group properties are calculated. ZL, ZL, ZT, and see for The governing load case is service load case, dead load, SIDL, live load. Loads at the pile cap bottom, including the load due to tilt and shift. No. Small, actually, we have taken even for the piles, small tilt is also considered. That moments are also included in this. And then we get a vertical load of 10,984, ML of 4,334, MT of 4,860. And then pile loads are calculated using this P by A, ML by ZL, MT by ZT. So we get a maximum pile load of 3768 kN and a minimum of 1725. And self weight of to this self weight of pile is also added because density of concrete is 25, and since this pile concrete is replacing a soil, we have taken only a net weight of the pile over and above the soil weight which is removed. This we have considered. This we have added to the maximum load, which gives a maximum load of 38887, which is about 390 tons, less than capacity of 400 tons. Similarly, minimum load on pile and lateral load of pile is calculated. Lateral load is distributed equally amongst all the 4 piles. And then using this formula given in IS 2991, for a fixed head, we have calculated this fixed D length as 6.748 meters. And then we have used this formula for fixed head to calculate the bending moment on the pile. And then the structural design of pile. So for the various combinations, we have calculated, we have got P, ML, MT. For ULS check, these are the maximum vertical load case, actually maximum moment case. This is maximum moment case. And this is the maximum moment case. And this is maximum, this is also a maximum vertical load, 2 cases and maximum moment case we have considered. And then for these cases, ULS moments and everything we have calculated. And SLS for the stress check, rare combination, and for the crack width check, quasi-permanent combination also listed here. With this, again using AdSec software, we have calculated ULS check and SLS check, and we find that it is this is the arrangement, and then we find that this is the capacity utilization ratio is 0.665. This is a maximum moment case. Here we have gone up to 0.665. And for the SLS check, the different combinations, we have got a maximum concrete stress of 5.22 and maximum steel stress of only -18, which are very less. And crack width is also 0, it's an uncracked section. Then pile cap design. So similarly, pile cap ULS bending moments are calculated at the face of the pier, both in longitudinal direction and transverse direction. You find these are the moments. 14,394 in the longitudinal direction, 14,979 in the transverse direction. And for this, we have calculated the bending moment, and the provided reinforcement is 25 mm at 125 centers. Then shear check, one-way shear check in the transverse direction is presented as it is more severe than the longitudinal direction. So we got the net shear force of 8,706 after reducing sulfate of the pile cap and soil above the pile cap. So BW effective width is 6,000, the full width of the cap width, and D, and maximum permissible shear force we have calculated as 42,125, which is more than 8706, and section is okay without any shear reinforcement. Then this is we have checked at even very near to the pile face by taking the critical section fear at the pier inner face, reduction factor alpha v by 2d 0.279, which is less than 0.25. So that means only a part of the pile load is coming as a shear. Only this 2432 is coming as a shear, and then we have using this formula we have calculated the shear resistance as 3031 more than 2432. Hence section is safe without shear reinforcement. Sometimes when the pile loads are very high, you will require shear reinforcement. See here the code says minimum pile cap thickness is 1.5 times the pile diameter. So we have used 1800 mm pile cap depth. Maybe if, whereas our pile load is only 400 tons. So suppose if suppose for some reason the pile load that we are coming is about 700, 800 tons, then definitely we would have required shear reinforcement. Whereas here, for this case, with a pile load of only 400 tons, we don't require any shear reinforcement. Check for two-way shear as per this clause of 112. And this is all the just what is given in IRC 112 is repeated. And punching shear check at the face of the column is done around the face of the pier. It is done effective for the total depth of 1800. We have taken an effective depth of 1700, and then perimeter of 6283, and then using all these formulae, we have calculated VD required is 1.364 against the capacity of 4.16 for the grade of concrete that we have used. Hence, section is okay in the punching shear. Just we have given a typical calculations which are required in the design of the pile and pile cap. And then we have calculated, we have checked the punching shear at D by 2 from the face of the column also with this formula. Then we find that here also it is safe without any shear reinforcement. And in fact, similarly, punching shear check around the pile also needs to be given where the section, control section is that here. We have to we have to check whether this is okay here. That is also, it is all right here in our case, where pile load is only about 400 tons and we have got a 1.8 meter thick cap, it is all right. It is not critical. But that check also needs to be done, and we have done that. And this is for that, this is the arrangement, and the drawings are shown here. This is a reinforcement, what is used in the pile. And this is the pier cap. Then a pier cap design. Calculations that are to be done for a typical pier cap design is presented. So this is for one of the projects. This is the type of pier cap that is adopted. The pier is about 2000 by 1500. This 1500 side, the cap is 5200, but other side is only 3700 against a pier size of 2 meters. So this is a corbel. The for this depth, though the depth is like this, but the depth is taken as a 1.8 meters for the design of the corbel. And these are the typical loads that that come from the bearings. They're all listed here. And for the various load combinations, what we have done is are shown here. And similarly, different combinations, lot of computations are required. And finally, end of the day, design forces, these are the design forces we have arrived at. And this is a typical design. So for the corbel, this is the B, AV. After removing the cover, everything, this is the depth, end depth, and this is the effective depth of the cap. Then check for corbel dimension. A by D in the this direction is 0.73 and this direction is 0.144. This direction is 0.73. This direction is 0.144. So both, which is less than 1. Hence, this is a corbel in both direction. For the corbel, end is to 0.9 and depth at the bearing edge is 0.9, which is should be greater than h by 2. But it is in our case typically it is h by 2. Hence, it is a corbel. And then these are the design forces. And then here check for shear is done based on this clause. And the shear stress is only 1.8 against allowable 4.75. Hence, it is okay in shear. Then calculation of the main reinforcement. These are the various steps given in IRC 112 we have used, and we have arrived at a reinforcement of 30,197 in this direction, 16,690 in this direction, and with a percentage of 0.48% this one direction and 0.19 in one direction. And then calculation of horizontal forces is done. Then enhancement factor for being close to support 2D by AV. All these things are calculated. And allowable shear force, shear stress is 1.25 in this direction and 4.61 in this direction. Whereas actual shear stress is only 1.8, 1.4, 1.2. Here there is no problem. Here there is a this thing, shear force for which stirrups are to be required. So here we require stirrups. Here we don't require because this is a very corbel, only horizontal stirrups are required. Here vertical stirrups are also required, which is calculated using this thing. And then there is another clause of it should be for minimum 50% of AST. Using this clause also, we have arrived at required shear reinforcement, vertical shear reinforcement as this. And then this is the 16 mm shear reinforcement is used. And then area calculated. And then horizontal reinforcement, stirrup reinforcement is to be provided within the top 2/3 of the corbel. That is also done. And this is the horizontal, this is the vertical stirrup reinforcement calculation also is done. And then this is a typical a drawing of the corbel.